Now that we know how to find an empirical formula from percent composition data, we're going to use the empirical formula and the molar mass of a compound that is determined by experiment to discover the actual molecular formula. So the empirical formula gave us a ratio. It said for every one carbon atom, there are two hydrogen atoms and one oxygen atom. But there are all kinds of combinations of that ratio that we could have that could tell us the actual molecule. And so, in order to discover that molecular formula of the actual molecule, we need to use both the ratio information that we have from the empirical formula, and we need to know the molar mass of the compound. And so, in this problem, it's telling us that they determined the molar mass to be 60 grams per mole. That is the actual molar mass of the compound. So let's write that in here first. So we're going to write in 60.0 grams per mole. That's what was discovered. Next, we're going to write in the molecular mass from our empirical formula. So it's not the molecular mass of our compound. It's the molecular mass of the empirical formula. By now, you should be really comfortable with calculating molar mass, but I'm going to walk you through it here just briefly. We would just add up the molar masses of each element multiplied by their subscript. So for carbon, it'll just be 12.01 times 1, so I don't have to do anything there. Add 1.008 grams per mole for hydrogen multiplied by 2, and we're going to add 16.00 grams per mole for oxygen multiplied by 1, and that gives us 30.026 grams per mole. So that's the molar mass of the empirical formula. And if we divide those two things, it gives us 60 divided by 30.026. It gives us 1.998 with no units because our units canceled out here. Now, why did we do that? Because we know that this is the ratio, but we also can see that obviously this does not match up with what was found. And so what we're going to do is see how many of these empirical formulas can go into the molecular formula. And hopefully that'll make a little bit more sense as we finish up the next couple of steps. So this is really, really close to the number 2. And again, we should feel pretty good about this because we can say, hey, our experimental data makes a lot of sense. It's never going to be perfect because there's always little tiny experimental errors, human errors that occur. And so this number is approximately equal to 2, and it's really close. So we're going to feel good about that number. And then we're going to multiply that by, we're going to multiply all the subscripts in our empirical formula by that number that we just found. So I'm going to copy that into here. We just change that blue for the sake of being clear. And so when we multiply each subscript by this number 2, let's come in here and, oops, let me actually copy this one so that it's already blue for me. We're going to multiply each subscript by this number 2. So the subscript right now for carbon is 1. When we multiply that by 2, we get 2. The subscript for hydrogen right now is 2. When we multiply that by 2, we get 4. And the subscript right now for oxygen is 1. So we're going to multiply that by 2 to get 2. And so this is our molecular formula. This is the actual molecule. So the ratios are the same. The ratios are 1 to 2 to 1, right? 2 to 4 to 2 is the same ratio as 1 to 2 to 1. But the actual molecule doesn't have just one carbon atom, just 2 hydrogen atoms, and just 1 oxygen. The actual molecule has 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms.